Section 12.3, maxima and minima of functions of several variables. I encourage you to go through the PowerPoint presentation and also open up your book to look at the various illustrations so that you can get a better feel for what you're actually doing here. And that is, you're going to be determining either relative minimums, relative maximums, or a new type of point called a saddle point. So a minimum would be like a valley in the mountain range, and the maximum would be like the peak of the mountain in the mountain range. And a saddle point is what the name describes. Why is it called a saddle point? Well, if you think about a saddle that you would put on a horse, this might be the part of it that's going up the horse's, beginning to go up the horse's neck. This is kind of the part that would go up on the horse's rear end. You would be sitting right here. Where do your legs go? Well, around the body of the horse. So this is neither a maximum nor minimum, and because of its shape is called a saddle point. All right, let's look at an example. Example number 1. So we're given this function in two variables, and the directions would be to determine any relative extrema and or saddle points that exist. Okay, so what we're going to do for all these questions is we're going to follow what is called the second partials test. Okay, we're going to be doing this for every single one of our problems. So the first thing is always going to be given to you. All right, I'm going to give you the function, and what you have to do is come up with the first partial with respect to x and the first partial with respect to y. And after you do that, you're going to set these things equal to 0, and then you're going to solve the system. Now, some of these systems are going to be a piece of cake, and some are going to be more challenging. All right, the good news is you've all solved systems of various types of equations in the past. So let's go ahead and begin that process right here. All right, so what that means is you look at your function, and this is something we did in section 12.2. First thing is, let's figure out our first partial with respect to x. So you're only deriving any term that contains an x. Every other term is to be considered a constant, which means the result here is just negative 4x, because the derivative of 1 is 0, and the derivative of negative 2y squared is also 0, again, because you're considering this to be a constant. All right, the next one, let's do first partial with respect to y. So now this is a constant. This is a constant. This is what you are deriving. All right, so you get negative 4y. Derivative here is 0. Derivative here is also 0. Okay, so what we're going to do now is we're going to let each of these partial derivatives be equal to 0. And we're going to create what is called a system of equations. Now, this system is very, very simple. If you think about it, there's no reason to use any substitution. You really can't use any substitution. So in solving this system, all you have to do is solve this equation for the single variable it's in terms of, which is x. So you get x equals 0. And the second equation is just going to generate y equals 0. They're not always going to be this easy. But what this is telling us then is you have what is called a critical point at 0, 0. Okay, so it's actually at f of 0, 0. All right, that's the critical point is the ordered pair 0, 0. But if you were to plug that back in to this function, you're either going to get a maximum, a minimum, or a saddle point. Okay, so to determine which one, you have to go through what is called the second partials test. All right, which is all this stuff. Okay, so the first thing I'm going to do is find what is actually called the discriminant with respect to the second partials, okay, with respect to a multiple variable, two variable function. All right, so in order to come up with these values, notice they're all second partials, hence why the name of the test is second partials test. Okay, so let's go ahead and do that. So your second partial with respect to x is going to be the derivative of this one, which is just negative 4. The second partial with respect to y is just going to be the derivative of this one, which is negative 4. And your first partial with respect to x, second with respect to y, is going to be based on this one, and now differentiating it with respect to y. So because you're now differentiating it with respect to y, this is considered a constant, so the derivative is just 0. Okay, so what the second partial test tells us to do is what? Well, this is what it tells us to do. So our discriminant is equal to what? It's going to be equal to the second partial with respect to x. Okay, and it's really of 0, 0, but the second partial with respect to x is just going to be negative 4 here because f of this value it's going to be constantly negative 4. So we can just go ahead and put in a negative 4. And this one, again, it doesn't matter what point you put in there. Doesn't matter because it's a constant value. So therefore, you just put in negative 4. Now, that's not always going to be true, but it is definitely true in this particular situation. The final part is looking at the first with respect to x, second with respect to y. We came up with 0. Again, it's a constant value. It's not going to ever change. And you square it. Okay, so what do we get here? We get that the discriminant, or our result of our second partials test, is positive 16. Okay, so now what do we do? Well, we look at the rest of this. And so what does it say? It says if the discriminant value is greater than 0. Okay, well, is this greater than 0? It sure is. Okay, so if it's greater than 0, we have to do another test here. We have to also look at the second partial with respect to x. So again, because your discriminant value is greater than 0, it's going to either generate a relative minimum or a relative maximum. Well, which one is it going to be? In order to answer that question, you have to now look at the second partial with respect to x value at the point 0, 0. Well, again, this is a constant. So it's always going to be negative 4. Because it's negative 4, we're looking at option number 2. Because negative 4 is less than 0. All right, so because this part and this part are both true in this particular example, then the function f, so therefore, f of our critical point equals something is what? A relative what? A relative maximum. Now, how do you actually determine the maximum? How do you actually determine the maximum value? You plug it in into your original function, which is right here. So you're going to replace this x with a 0, this y with a 0. You just get 1 minus 0, which is 1. So the value 1 is actually the relative maximum, 1. All right? The whole ordered triple point would be 0, 0, 1.